So we first define the infinitesimal generator of a semigroup. And so it's defined, first you have to define the domain of the operator A. So the domain will be the points in X where you got this limit. So this is the analogous to the definition of a derivative, right? If you had a function from R to R, and the right hand side derivative, the right derivative of this function. So the points X where this limit exists is the domain of A, which we denote by D of A. And subsequently, you will have that A of X is this limit. So we also say that in this case, A generates S of T. So this is a general definition for the infinitesimal generator of a semigroup. In this definition, you don't need, you don't talk about uniform continuity. So next, we consider the case of generators of uniformly continuous semigroups. And we have the theorem, a linear operator A is the generator of a uniformly continuous semigroup if and only if, in fact, D of A is X and A belongs to the set of bounded linear operators on X. So let's have a look at the main points in the proof. So of course, the point is first we want to prove that D of A, so we assume first that S of T is a uniformly continuous semigroup. And we want to prove that this limit exists for all X. So want to show that D of A equals X. To do so, we first start by proving that if my row here is small enough, then this thing, this operator will be invertible. And how do we do that? So we look at this quantity, and by a small computation, we can see that as rho goes to 0, this thing goes to 0, meaning that if rho is small enough, you will have this is less than 1. But if this is less than 1, this means that this is invertible. I let you this question as an exercise. All right, now, when we know that this is invertible, you can do some computations, and by using this change of variables first, you do some tricks, and you arrive at this formula here. But now you can take the limits. This here will converge to S of rho. This here will converge to identity. Then finally, you get that A is defined like that. And so we have proved by doing this that this limit exists in the set of the bounded linear operators. So yeah, so this implies that it also exists for all x in X. All right. So the fact that, and since we have the convergence in the set of the bounded linear operators, it's also a small exercise to show that in fact A is also bounded, is a bounded linear operator. This comes from the fact that this is the convergence in the norm of the bounded linear operators. So all of these are exercises that I leave to you. Now, conversely, if you assume that A belongs to L of X, you will define S of T as this series. So this defines a semigroup. We have already done that with A matrix, so this is exactly the same. Then by simple computation, you can prove that S of T converges to the identity when T converges to 0 in the operator norm. And there's one thing that remains to discuss about is, so we need to prove that A is the generator of S of T. So you need to consider here this thing. And again, by computations, you can prove that this goes to 0 as H goes to 0. And that's it.